Okay, so this is your first intro into pure calculus, all right? So guys, I'll tell you right now, in calculus AB, we do only two things. Take a derivative, and we take an integral, okay? You might not even know what those words are yet, but these are the only two things. Now, yes, we do it many different ways, but there are only two things. When my students take the AP exam, I tell them, look, if you don't know what to do, there's only one of two options. You're either going to take a derivative or you're going to take an integral, okay? So today we're going to start very, very easy. We're going to start talking about derivatives, okay? We're going to start talking about derivatives. Now, there are several different ways to take a derivative of a function, okay? There's a long way involving limits, which I am going to show you after I show you the shortcuts, okay? So I'm going to start with the shortcuts, and there's a reason I do that, okay? So I'm going to start with the shortcuts. So the first shortcut we're going to talk today is the power rule, okay? So something called the power rule. And we'll get into that in a little bit. But first, let's talk about a derivative. So this is kind of like a definition. I do want you to write this down, okay? It says, what is a derivative? Simply put, the derivative can be interpreted as a bunch of things, okay? The slope of a tangent line, okay? The instantaneous rate of change of a function, and an instantaneous velocity of an object at a specific time, okay? So, when we take derivatives, guys, we're talking about one of these three things. We're talking about a slope of a tangent line, the instantaneous rate of change of a function, and perhaps the instantaneous velocity of an object at a specific time. Has everybody taken physics or is taking physics? Right? So once we get to this part, the instantaneous velocity and rate of change, you're going to see that because you're doing that probably in physics. And it might probably make more sense here, okay? Because we do it more algebraically than anything. But, so these derivatives, guys, first I'm going to show you how to do it function-wise, you know, with a bunch of equations and blah, blah, blah. But then we get into more the application of derivatives, which has to deal with rate of change and velocity and all that good stuff, okay? So, today we're going to concentrate on this part, the slope of a tangent line. So first of all, I'm talking about what? A slope of a line. Does anybody know what tangent means? Okay, so there's a tangent actually has a couple meanings. So you are correct. Tangent in pre-cal, when you're talking about the word's escaping me right now. Sine, cosine, and tangent, all that good stuff. What is that called again? Trig. Golly. When you're talking about trig, so tangent does exactly what Jordan said. It's sine over cosine, correct? But I'm talking about the definition of tangent. So I'm just going to draw something here. Okay, I'm just going to draw something here. Okay, so say that is a function, correct? Say that is a function. Now, when I say tangent line, okay, when I say tangent line, a tangent line is simply put a line that touches any function only once, okay? It can only touch it in one place. Like, for instance, okay, does everybody agree that that's a tangent line? It is only touching it once there, right? So because it's a line, it does have a what? Has a slope. It has a slope. In this case, could you tell me a little something about this line slope? It's at least what? You should be able to tell me it's at least positive. Now, is this slope of this line on this function always going to be positive? No. You guys notice that if I kind of move along my line over here, say for instance down here, that this slope is what? Negative. And as I continue, maybe even somewhere down here, this has a what we call a zero slope or a horizontal slope, right? Okay, and then so you realize that I can basically, now notice what's the difference is I'm looking at the slope, the different tangent lines at a certain point, right? At a certain point. I'm only looking at this point or this point or this point, okay, or this point. So when I take a derivative of a function, it's the slope of a tangent line at a certain point, not all the time. Okay? Not all the time. So that's what we're going to do. You notice that even here, it's still positive, but it's more positive than this one, correct? Right? So it changes. It changes as I go along this function. It changes as I'm moving along. Okay? So now, how do I find that? Well, we're going to start with one of the rules. There's 4 shortcuts, and then there's a long way. Okay? I'm going to show you the 4 shortcuts first. Okay? The first one today is the power rule. So, before we get into the power rule, however, let's talk about some properties. So copy these down, and then we'll talk about them here in a bit. Let me start recording. Okay, so these are your properties of derivatives, okay? So now, first of all, I want to pull out some things. It kind of probably looks like Chinese as you're looking at it, right? But look, there's something. You see this right here? That little apostrophe? Okay, that is called prime. It's called prime. So the way I would say this is I would say f of x plus or minus, right, g of x prime. What prime means is take the derivative, okay? Or the derivative has been taken. Okay, so when you see that little apostrophe, that means the derivative. You're taking a derivative. Okay, so now this first property, what this first property says is this. If I have 2 functions, right, I'm going to call them f and g, and I'm adding or subtracting them, and notice they're in parentheses, so they're together, right? So what this first property says is this. I can basically split them apart. I don't have to take it all together. I can just say, look, I'm going to take the derivative of the first part and then add or subtract the derivative of the second part. Okay, I don't have to do it all at once. I can just do piece by piece. Okay, so this one's more do it piece by piece rule. Okay? This right here means the exact same thing. I'm showing you, what the point of this slide is I'm showing you all the different ways that they can tell you to take a derivative. See this right here? d dx. This means the derivative with respect to x. So this means you're taking the derivative with respect to x. Now, you usually always take a derivative with respect to x anyway, okay? But I can, and later on in the class, I will change this to d dy, right? Saying I'm taking the derivative with respect to y instead of x. So the thing is, I can change this to anything, right? I can change this. What if there are no x's in my function? Then it would be whatever it is, right? If it was s or p or m, remember they're just variables, right? So I can take any derivative with respect to any variable. And basically, this rule is saying the same thing as this rule, right? If I'm taking the derivative with respect to x of these 2 functions together, essentially I can split them up. I can take the derivative of f with respect to x plus or minus the derivative of g with respect to x. Does that make sense? So basically, if you have a long equation, a long function, right, you can basically just look at it piece by piece. That's essentially what I'm trying to get to you here. Okay, the third one here, it says this. C of f of x prime is equal to c of f prime of x. Basically, c here is a constant. C here is a constant. So it's saying this. If you have a function that's being multiplied by a constant, what essentially you can do is pull that constant out, okay? Make it smaller. So say I had this function that was huge, large numbers, and everything was multiplied by 100, okay? They're saying, okay, look, just take out the 100, do your derivative, and just keep that 100 there in front, okay? So basically, that's what this is saying. It's saying, if I have a constant times some function, and I need to take the derivative, I can pull out that constant and then just take the derivative of that function. It's basically like reducing it, right? And this is saying the exact same thing with respect to dy dx. And then finally, my last rule is this. If your function is a constant, like y equals 2, if your function is a constant, then its derivative is equal to 0. Then its derivative is equal to 0. And it makes sense because remember what I told you, a derivative is the slope of a tangent line, right? The slope of a tangent line. And if your function is a constant, so think about when I showed you down here, okay? It's a constant, meaning it's not increasing or decreasing, right? It's constant, which is happening at this point. Look at its slope. It's what? 0. Okay? So, those are the semantics. Now let's get into the power rule. Here is the actual rule. Here is the actual rule. Again, I'm going to let you copy this down. I'm going to write it up here bigger because you might not be able to see this. Alright, so what this rule is saying this. If you have some function and it's x to any exponent, right? That's why it's called the power rule, because we're dealing with powers. We're dealing with exponents. The rule is very simple. It says here, then its derivative is, now notice what happened. Tell me what happened. I got my exponent and I put it where? In front. So I got my exponent, I put it in front. That's why it's the n in front of x. And then notice what I did to my exponent. You subtract 1. Very simple. Very simple. Let me give you a very simple equation. So if I told you this, if I told you here's your function, x to the third power, x to the third power, right? Then its derivative is, now tell me what to do. What happens to my exponent? It goes where? To the front, so it would be 3x, and then what do you do to your minus 1? So it becomes squared. That's it. That's the power rule. That's the derivative. So, the derivative of this function is 3x squared. Okay, what does this mean? This means that at any point on this graph, the slope of the tangent line is going to be this. So if I wanted to find out, okay, what about the point where x equals 2? So what do? I just plug in 2, right? So it would be 12. So the slope is 12, positive 12. Okay? So that's the whole rule. Now, what happens when I get to, let's look at A. Let's look at A. Okay? Because that's an easy one, right? That one's an easy one. Let's see what happens over here. Okay? F of x is equal to 15x to the 100th power minus 3x to the 12th power plus 5x minus 46. Now, so here, I don't have some simple just x to the third power. I have a bunch. But what did our first property say? I can do it piece by piece. Do I have to look at this whole thing? No. I can just look at the first part, and then I'll move on to the next part, and then I'll move on to the next part, and so on and so forth. Does that make sense? So don't look at it like like this long equation, although yes it is, right? But don't look at it like that because you're going to drive yourself nuts. So just look at it piece by piece. Now, what do you think I do then if there is already a number in a coefficient? If there's already a coefficient, you're just going to multiply. So that x, so let's look at this first part. 15x to the 100th power. So just looking at 15x to the 100th power. What do I want to do? Bring my exponent to the front, but there's already a 15 there. So what do you think I did? Multiply. So what's 100 times 15? So you're going to get 1500 x to the 99th power. Is everybody good with that? Now move on. Minus 12 times 3 is 36. X to the 11th power. Now this is interesting. This is interesting because on this term right here, what is the exponent? 1. Okay? It's a 1 right now. So then 1 times 5, of course, is 5. But then what happens to my x? Because it becomes x to the 0 power. Anything to the 0 power is what? 1. So what happens to my x? It kind of goes away, right? Because it's technically 5 times 1. But do I have to write times 1? No. Okay, plus 5. And then minus 46. What did our last rule say? That the derivative of a constant is what? 0. So then the derivative of minus 46 is what? 0. So do you think I have to write plus 0? No. So guess what? That's it. That's my derivative. My derivative is 1500 x to the 99th power minus 36 x to the 11th plus 5. You okay with that? Yes. It's a constant. So anytime you have a constant, the derivative of a constant is 0. Okay? Everybody understands what I mean by constant, right? No, there's no variable. So any number, the derivative of any number, I don't care what the number is always 0. So the derivative of this part is a plus 0. Okay? But I don't have to write, of course, plus 0. Any questions so far? Pretty simple stuff, right? And you're like, this is calculus? And it's like, yeah, it's not that difficult. All right, so now let's pick it up a little bit. Let's look at part B. I have g of t equals 2t to the 6th plus 7t to the negative 6th. 2t to the 6th plus 7t to the negative 6th. Okay, so g prime of t, which, again, what does that mean? That I have taken a derivative. That I have taken a derivative. Okay, a derivative has been taken. Is equal to what? 12t to the 5th. Everybody good with that one? Okay, and then? So Vanessa's saying minus 42. Does everybody understand where she got that from, right? Minus 42 what? T to the negative 7. Again, everybody understands where I get that negative 7 from, right? Any questions so far? We good? Okay, pretty simple stuff, right? Now here's an issue. Here's an issue. We don't like negative exponents, right? Does anybody remember how to fix a negative exponent? Put it over 1, and you're going to do what? Take a reciprocal. Essentially, you're going to move it to the bottom. But only that thing, okay? But only that thing. So this 12t to the 5th, it's fine, right? It's fine. It doesn't have any negative exponents, so I'm going to leave it there. Now, here's where most students will get confused. I have a negative 42t to the 7th. Guys, what's the thing that has the negative exponent? Just the t. Because remember, these are multiplying, right? This technically means negative 42 times t to the negative 7. So the only thing that has the negative exponent is the t. So what's the only thing that goes down to the bottom? Just the t. So then, therefore, what stays up top? So it would be minus 42 over t to the now positive 7th power. Do you guys remember that rule? Right? It was an algebra 2 rule, I believe. So this is your final derivative. Simplified, made perfect. Okay? So, does everybody understand what I did here? Right? With the negative exponent? So basically, because remember, the rule was technically you put it over 1 and take the reciprocal of it to make it positive. So that's all I did. I just took it to the bottom. Okay? Any questions on that? Okay, let's go to part C. Let's go to part C. Now, just looking at it, do you guys see where we might have an issue? Right here, right? Right here. Because I didn't teach you how to do a derivative of a fraction yet, right? But same concept over here. Couldn't I use the same thing over here? Okay, so can I rewrite this? Before I even take the derivative, can I rewrite this to help me? Yeah, I can. So this is not a derivative. This is just rewriting. So rewriting, this would just be a z to the 3rd power. What do you think? Remember, which one's the only thing that goes to the top is the what? So good. So it's a minus 1/3 z to the negative 5 plus z minus 23. Do you guys see what happened over here? So what some of the students were saying was, oh, it just becomes the 3z goes up top. Why does the 3 not go? It doesn't have a negative exponent. Or I'm sorry, it doesn't have the exponent. The only thing that has the exponent is the z. Okay? When would I take both? How? How would that even look? Good. It would have to be in a parentheses like that, right? In order for you to take both. But it doesn't have it, so then I only take the thing that does. We good? Okay, now can I take the derivative? Sure. Okay, let's take the derivative. Okay, so 8z to the third power. What's its derivative? 24z squared. You with me? Next part. Negative 5 times what? Negative 1/3. So a negative times a negative is going to be a positive. What's 5 times 1/3? 5/3. Right? Z, negative 6. Okay? Plus, what's the derivative of just z or x or anything? Think about what's up here. A 1. The 1 moves to the front, so there is a 1. And then what happens to my z? Goes away. So the derivative of z or x or anything is just 1. And then what's the derivative of minus 23? So then, don't worry about it. So is this my final answer? No. What's the problem? The negative. So all I got to do is fix that. So I get 24z squared plus, how do you think this one's going to look? Good. That 3 is there on the bottom, so put it back. 3z to the 6th power plus 1. So again, I'm finding derivatives. What am I finding again? The slope of the tangent line at a certain point. Okay? It's the slope of a tangent line at a certain point. So, if this was my actual function, like if you were to actually graph this thing, right, it would be a weird graph. And just like this, it would look something like this. It would look something like this. Okay? Just some curve. And basically that what you just found, the long equation, is a formula. So everywhere at this x, say this x was 2, I would plug in 2 to that formula, and I'd get a number. Because remember, slope is just a number, right? It's a rise over run. So I would get a number, and whatever number is, that is the slope at that point. Okay, you have to understand what you're finding here. Any questions so far? This is very simple, right? It's called the power rule. The reason it's simple is because it's the shortcut. I'm showing you the shortcut first. Okay? I'm showing you the shortcut first. Let's try again. Okay? So, I threw a little curve at you, because have I talked about radicals at all? No. But does anybody remember any rule from Algebra 2 that might help us out? Good. A radical, guys, a radical is nothing but an exponent, a fractional exponent. Y'all remember that rule? So, okay, let's talk about this, okay? So this is not for this problem, this is side note, okay? This is side note. Do me a favor. Everybody knows what's the square root of 4, right? It's what? Technically, but yeah. Right? Technically plus or minus 2, but yeah. So if you were to put this in your calculator, you would get 2 as an answer. Agreed? Okay, do me a favor. Put this in your calculator. Yeah, so that's the third root of x cubed. Or no, x squared. This is a 2. 2, sorry. Okay, so what's 4 to the 1/2? 2. Do me a favor, what's 25 to the 1/2? If you put it in your calculator, you're going to get 5. What's 16 to the 1/2? 4. So, do you guys catch anything? What? It's the same. So the rule is very simple, guys. The rule is this. The square root of anything is the same as that anything to the 1/2 power. Okay? To the 1/2 power. Except it doesn't only apply to square roots. It actually applies to any radical. Any radical. What's the exponent of this x here? 1. And what root is this? Technically, it's a square root. So look, here's the other rule. Say I did a cubed root, and it was x to the fourth. What do you think it's going to be? X to the 4/3. Does everybody see how that works? The rule is this. The rule is this. The rule is this. So m x to the n, okay, is the same thing as x to the numerator over the n. Okay, so whatever the radical is, the root of the radical is the denominator, and the exponent of the inside is the numerator. Okay? So this is my rule. Something you should have learned in Algebra 2. Okay? Got to remember this. You're going to use it all the time. Basically, I don't want to deal with radicals. I'm going to just deal with fractional exponents, because if I can deal with an exponent, I can do my power rule. Okay? We okay? So now, keeping that in mind, can I do something then with this with these radicals in my equation? Yeah, I can make them not there, basically, right? So, let's rewrite my function. What is my function going to really be? X to the 1/2 power plus 9x to the 2/3. You with me? Minus, let's see how quick you are. Good. 2x to the negative 2/5. Do you understand why she made that negative? Any questions on why she made that negative? Because where was it? In the bottom, and I don't want them in the bottom, so in order for me to take it up top, I have to make it a negative. Is everybody with me on that? Yes? Okay, so now, look what I have now. Nothing but what? Powers. I have nothing but powers, so guess what I can use? My power rule, right? Because it only applies with exponents, with powers. So, let's see how good your math is with fractions. So now, my derivative is what? What happens to this? Goes up front, so 1/2 x to the negative 1/2, right? 1/2 minus 1 is a negative 1/2. We good with that? Okay. Plus, so 2/3 times 9 is 6. X to the negative 1/3. Now what? A negative times a negative is a positive. Try that again. 4/5 x negative 7/5. So guys, how many of you struggle with fractions, adding and subtracting? Get used to it, because this is a lot. We do it a lot, okay? You got to learn how to multiply fractions. You got to learn how to add or subtract very quickly, okay? All right, so now, is there a problem with my answer? This is my answer. I'm essentially done. Is there a problem with it? What? The negative exponent. So I can fix that. And however, so I'm going to fix that. So basically, as everybody realizes, I'm going to take a bunch of reciprocals here, right, to make them positive. However, it's also kind of, this is the way I like to explain it, okay? How many people speak Spanish in this classroom? Okay, more than half, right? So if someone comes up to you speaking Spanish and only Spanish, right? If they come up to you speaking Spanish and you answer them in English, it's kind of rude, correct? It's kind of rude, right? And vice versa. If you speak Spanish and I speak English and I come up to you speaking English, when you speak Spanish to me, it's kind of, I'm like, first of all, I don't understand what you're saying, and second, it's kind of rude, right? So guys, it's the same kind of concept in math. Notice how they posed my question. They asked me in radicals. So I have to answer in radicals. Does that make sense? So I switched it for my benefit. So that's why I think of Spanish, because when I speak Spanish, the first thing I do is translate in my head, which is, I know, the wrong way, right? But that's what I do. I translate what you just told me in English, I process it, and then I try and put it back to you in Spanish. Does that make sense? And that's what we're doing. So they spoke to us in radicals. We translated it to exponents so that I could do the work, right? But then when I answer, I have to put it back in radical form. Does that make sense? So this 1/2 is going to go down to the bottom, but I got to switch it back to a radical. Can you tell me what it's going to be? Square root of x, right? So it's going to be 1 over 2 square root of x, because that 2 is already there at the bottom, right, with that 1/2. Is everybody with me? What about the next one? Does the 6 go to the bottom? No. So it's going to be 6 over cubed root of x. You with me? Plus 4 over 5 fifth root of x to the 7th. And that is your final answer. This is the derivative of t. You know what I like about calculus? What I like about calculus is, was this very difficult for us to find? Like the math was not that difficult, right? But my favorite thing is, like, everybody saw Miss Ash come in. My favorite thing is like when administrators or other adults come in and they just like look at the board and they're just like, never mind, and just kind of walk out, because it looks like Chinese, right? I mean, literally, they don't understand what we're doing. But so it look like, that's what I like about calculus. Calculus can make something look terribly, terribly hard, but actually, if you understand it, it was pretty simple in the first place. Okay? All right, we'll finish the rest on whenever, Thursday. Okay, we'll finish it on Thursday. I kind of want to let this sink in a little bit. Feel free to go again over your notes, and I'll talk to you on Thursday. All right?